Exponential growth in decay models. Population growth. For uninhibited growth, the formula is n of t equals n sub 0 e to the kt, where k is greater than 0. Here, n represents the number after time t is time, n sub 0 is the initial population, k is a positive constant representing the growth rate. So let's look at our first example. The number n of bacteria present in a culture at time t in hours obeys the law of uninhibited growth, where n of t equals 1000 e to the 0.01 t. First, determine the number of bacteria at t equals 0 hours. So n of 0 is equal to 1000 e to the 0.01 times 0, because we're substituting 0 in for t. We get n of 0 is 1000. And we could have identified this as the constant that we had in our initial formula, 1000. Second, let's find the growth rate of the bacteria. Okay, well, given that our formula is n of t equals 1000 e to the 0.01 t, this 0.01 is our growth rate, and that corresponds to a growth rate of 1%. Next, what is the population after 4 hours? So now we're going to substitute 4 in for t. So n of 4 is equal to 1000 e to the 0.01 times 4, which is 1040.810774, or approximately 1041 cells. Next, when will the number of bacteria reach 1700? So given our original formula, n of t equals 1000 times e to the 0.01 t, let's substitute 1700 in for n of t. So 1700 equals 1000 e to the 0.01 t. And now we're going to solve for t. So the first thing we need to do is divide both sides by 1000. 1.7 equals e to the 0.01 t. To solve for t, we're going to need to rewrite this in log form. This will be log base e, or natural log, of 1.7 equals 0.01 t. Divide both sides by 0.01, and t is equal to 53.0628, or approximately 53 hours. Finally, when will the number of bacteria double? So our starting formula was n of t equals 1000 e to the 0.01 t. So if 1000 doubles, it will become 2000. So let's put 2000 in for n of t. Let's solve for t like we just did. So we'll divide both sides by 1000. And we'll get 2 is equal to e to the 0.01 t. We will now rewrite this in log form. So log base e, which is the natural log, ln of 2 equals 0.01 t. Divide both sides by 0.01. And t is approximately equal to 69.31471806, or about 69.3 hours. Okay, let's also look at radioactive decay, uninhibited. Here the formula is practically the same. A of t equals a sub 0 e to the kt, but here k will be a negative constant. It will be less than 0. Here A represents the amount after time t, t is time, A sub 0 is the original amount, and K is the decay rate, which is the negative constant. So let's look at our second example. The half-life of radioactive potassium is 1.5 billion years. If 10 grams is present now, how much will be present in 100 years? So first, we need to figure out what K is. Our formula will take the form A of t equals A sub 0 e to the kt. We know our original amount, A sub 0, is 10, and we're given that A after 1.5 billion years is 5. Substituting this in, we get 5 equals 10 times e to the k times 1.5 billion. Divide both sides by 10, and 1/2 equals e to the 1,500,000,000 times k. We'll rewrite it in log form. Log base e, which is the natural log of 1/2, equals 1.5 billion times k. Divide both sides by 1.5 billion. And we get k is equal to negative 4.62099812 times 10 to the negative 10, or negative 0.000000000, that's 9 zeros, 462099812. So our formula now becomes A of t equals 10 times e to the negative 0.00000000046099812t. So we want to know how much will be present in 100 years. So we will substitute 100 for t and get approximately 9.99999538 grams. So very little will decay.